Something that I think affects us all. I hope to convince you that this affects us all. We've been thinking a lot lately in my group about abstraction, right? A principle in computer science that we are all very fond of, right? And I think, bear with me here for a second, but what I really want to talk about is how that is starting to, how the breakdown in abstraction in modern machine learning is starting to affect our scientific inferences. So what do I mean by abstraction, right? So we think about a model, right? We think about a statistical model, a machine learning model, something like this, and we think, okay, it's running on some underlying infrastructure, but the modern cloud architecture or CUDA or whatever is so good that we don't have to worry about that particular hardware instantiation. Any of you who has ever gotten caught in CUDA driver hell knows that that's not a thing, but bear with me, we think that's a thing. Optimization, right? So we think that optimization, we stipulate a model and then we say, I'm going to optimize this model, and thus optimization is an abstracted object that we call, and it doesn't bring its own kind of biases to the party. That's the way things are supposed to work. And so too, if we're doing a probabilistic inference, Bayes' rule is something like this. We also think about the same thing there, right? We just appeal to Bayes' rule, inference is taken care of. It's a great abstraction. You learned about this, and when you learned about it with GLMs or with convex optimization or whatever, that was true, yeah? Now, in modern machine learning, we're realizing how much that's not true, right? So we've all heard a lot about stochastic optimization, sometimes called the naive genius of stochastic optimization, and how it confers inductive bias onto neural networks as a regularizer. There is also a reproducibility crisis in machine learning. If you haven't read about it, you should. Essentially nothing, you can't reproduce any of the results that you find in papers, right? And the kind of naive notion that a GitHub repo will do it, even a properly set up Docker container can't always get there. So inference is what I want to talk about today. The fact that inference, now of course we know that when our models get big enough, we have to appeal to something like an approximation. Approximate inference is kind of one of the cornerstones of probabilistic machine learning. But that abstraction, I hope to convince you today, is leaking into our science. All right, why should we care about this, right? Well, I don't want to be too Bayesian today, but I am going to talk about probabilistic reasoning. The whole point of probabilistic reasoning, I'll go over this sort of in more detail, is that we have this object and we have this formalism via Bayes' rule to go from a prior belief, a set of data, to a posterior belief about the world, right? And as inference becomes approximate, it changes that belief state, right? How it changes that belief state is going to have meaningful impact on the things we try to do, the statements we try to make about the world. If we're doing something like model inference, unsupervised learning, learning latent variables, etc. Why do I care about this? I care about this a lot. My group cares about this a lot as an object, cares about inference as an object of scientific inquiry, by which I mean there are models. A lot of my group is involved in computational neuroscience. I realize I have brought neuroscience to a protein party to some extent, so I'm not going to talk too much about proteins, but it's fine. There are well-developed biologically motivated models. You don't have to worry about this. These are different cell types. We are particularly interested in inferring something about the state of these excitatory neurons in a brain system. And so when we have this model, we collect a bunch of data. We have to do approximate inference. The statement we get back, ideally, that is a real thing about the brain. We have learned something about how the brain operates, how the brain responds to a particular stimulus, et cetera, right? If what we're actually learning is some biases of our approximations, that's kind of stupid, right? Yeah. All right. So we've also done a bit of, I'm going to talk about probabilistic inference in kind of the classic sense. We've also done a bit of this for conditional diffusion, conditional diffusion, excuse me. This came up in the last thing, so I just wanted to throw in a quick slide about this. This is a hastily put together slide during the coffee break. So a quick minute on conditional diffusion. Jen made this comment about how using guidance to do conditional sampling feels a lot like Bayes' rule. And that's absolutely right. When you have an unconditioned diffusion model, P of x, if you have a likelihood, P of y given x, you can use that as guidance, essentially as this gradient signal to push you towards a posterior sample. In the discussion that came up, there was mention made of twisting and sequential Monte Carlo, and the deep history that this touches in statistics, statistical mechanics, Markov chain Monte Carlo, and other things. I mean, like essentially what all this boils down to is it should not be a surprise that there is a ton of work, I mean, generations and conferences, et cetera, on propagating samples from one density to another, right? Which in the end is what conditional diffusion is. So John and I were talking about this a few minutes ago. Like, diffusion is at this time where everybody gets to bring their favorite toy to the party, right? And one of the things that is happening there is people are saying, wait a second, we're propagating one density to another over a sequence of time points or a sequence of intervals. So we've got all of these tools to bring, right? One of those is sequential Monte Carlo, where essentially the idea is instead of just injecting that one guidance gradient, you are doing via this algorithm, which if you think about it as particle filtering, you're essentially exactly correct. You add a gradient, then you do an update, propagate that forward through time, do a correction step, and then repeat at each of your time steps, right? I don't really need to go through this. There is a neat paper that a student of mine, some of you might know Brian Tripp, he's been on the job market. Luhan Wu, she will be coming to the job market soon. She's an amazing student. If you want to learn more about this, you should have her give a talk on that. Cool. I think that covers it. But just to say that this is a really rich area right now. You mentioned a lot of the cool papers on that. We talked about a lot of the cool papers on this. There's connections to Hamiltonian Monte Carlo as well. This is really a rich time for this. Is twisted SMC the right way to do it? It is a right way to do it. HMC is a right way to do it. It is worth our time to spend some effort trying to connect back to all the work that has been done in this space. Cool. All right. Have I kind of legitimized myself in the protein room now? Okay, cool. Great. I'll go back to other stuff now. No, Jen told me, she was like, you can't continue your talk unless you say something about proteins. All right. Okay, so probabilistic machine learning. I said some vague things about abstraction here. Let me make this one step more concrete, right? I'm no great fan of Bayes' rule, but it is quite elegant in its simplicity, which is it says, like in some kind of fundamental sense, it's unassailable, which is if you treat all of your unknown quantities as probability distributions, then you can just appeal to the magic of Bayes' rule and let it do the rest, right? That is like going back philosophically the idea of inverse probabilities. So what do I mean by that? We're going to talk, for reasons that will become clear, about reasoning over some state of the world F, okay? That is we start with some prior belief. We also are endowed with a belief about how that state gives rise to data in the world, right? A likelihood and observation function, something like this. We're going to collect a bunch of data. We are then going to put that together through the magic of Bayes' rule. And I do mean magic in the sense of like, this is a crystal ball, this is an oracle, right? You put these two things in with a data set, you get out an updated belief state about the world. Now, why is that so important and why am I dwelling on this? Because notice the beauty of that is it says model plus data gives me an updated belief about the world, right? That is kind of one ansatz of AI for science, right? Is that we can do that. We bring a model. It is a tool. It is an instrument, just like any other instrument, any other scientific piece of instrumentation. And if we have data, we can put those together and learn something about the world. Okay, that is as true whether f is an individual variable or whether it's a function of some inputs x. How do we deal with this, right? This is hard. As soon as you learn about the magic of Bayes' rule, you learn that we need to approximately solve it, right? Because Jen was taking pot shots at conjugate models before, right? This is just like, it's great. These are good, useful toy models, but then when you actually need to do something scientifically relevant, you are in a non-conjugate land, you're in a computationally expensive land, so you need to appeal to something else. Oh, shout out again to Hamiltonian Monte Carlo. One way of dealing with that is to say, let the abstraction work, right? I'm a computer scientist, I'm a believer. You say there are probabilistic programming languages, PPLs like Stan and Pyro, that give you a structured language to write down this model, and then under the hood it says, I'll take care of the inference, right? Now, it doesn't actually do that, right? It uses Markov chain Monte Carlo type techniques, maybe increasingly variational inference. So the point is, it's pretending that it's abstracted that away, but it also has all these own biases going along. Okay. What else? This comes up all over the place. I'm writing this as simple models here. There's plenty of places where we blur these lines even further, right? So even down to their names, right? Like a variational autoencoder, a GAN, invariant risk minimization. These are things that even in the writing of the papers, we can't quite decide whether it's a model or an inference technique. So the point of this talk, and the point of what I'm saying here, is just that as inference gets more and more approximate, it is not okay to consider it separate from the model, right? This crystal ball is obviously not a crystal ball, and we ignore it at our peril. So, yeah, we go to bed at night knowing that MCMC, ABC, VI, BBVI, these type of things, these are not the same as this crystal ball. They're a mess, right? So the crystal ball is not a mess. It's actually a computing machine, right? It's this kind of weird pixelated robot that is making assumptions and choices all of its own, right? And we have not accounted for them. This is particularly offensive because the whole point of Bayesian machine learning or probabilistic machine learning is to instantiate all of our unknowns as probability distributions. And yet, like, the computing that is done in the center of this, we're just like, nah, just hide it, right? And that has real consequences. The real consequences is the updated belief, the scientific inference that we make, is now not a statement about model and data. It is a statement about model, data, and some other stuff that I haven't bothered taking care of. Right? That's the point of today, right? The point of today is how to rationalize approximate computation probabilistically. Sorry, the point of my talk today, not your whole day. All right. I will introduce an example model here. I'm going to talk about Gaussian models because they are tractable in a particular sense, a Gaussian process model. Okay, if you've seen a Gaussian process before, I'm not going to do anything particularly fancy with Gaussian processes. The reason I'm choosing Gaussian processes is because they are a sufficiently complex probabilistic model that we always have to appeal to approximate inference. Right? You can't do anything with a Gaussian process in the modern world. It's just too expensive. Right? However, they are also a model that really boils down to just linear algebra. And if there's a thing that we know how to really understand in computation, it's linear algebra. Right? All right. If you don't care about Gaussian processes, cool. I don't want you to think that this is a talk about Gaussian processes. I want you to think this is a talk about this problem of computation in approximate inference, and that Gaussian processes are just a handy model to run through for today. All right. So a Gaussian process, just notation slide. We have xy pairs. We're trying to learn a function that maps x to y. For convenience, this will be a regression problem. I don't, none of this will really matter. We say that f is distributed according to a Gaussian process with some mean function mu and covariance kernel k. What the fundamental definition of that is that any subset of the function f, in other words, take n input points, x1 to xn, evaluate that function and get this vector. That vector has a Gaussian distribution, is a Gaussian random vector with distribution mu and k, where mu and k is normal mu k, where mu is the mean function evaluated at those points, and k is the covariance function evaluated at all pairs. Okay. Great. What does this look like in practice? In pictures, we say a Gaussian prior. This is a common representation. A Gaussian process prior will look like this. In other words, I've seen no data, so I have something like mean 0, and I have some covariance around it. Right? This is my belief state about the world. This is my prior. Right? I know nothing, and I have uncertainty about what little I know. Now I'm going to start collecting data. I'm going to do that, again, using Bayes' rule. Right? If I have this likelihood that says, given some underlying function, right, I just add some Gaussian noise to that, and that gives me data. I'm now going to query about test points, right, new points x in the world. That induces a posterior that is also a Gaussian. So here's the linear algebra piece, right? Gaussian conditioning, you suffer through that once in your life. It ends up looking like this. Mu star, your posterior mean, is mu plus this function of the kernel. This is the core object that is painful, right, which is a linear solve, right? Linear algebra, Cholesky, conjugate gradients, all these type of things, right? You've got your observations. You solve those against the covariance kernel. You map those back out to the new data point, and that influences your mean function. You do the same thing with the variance, and off you go, like this. You've observed a data point. This data point happens to be around 0, right? So this is x, this is f. Right, we've gone from that prior belief to now when I observe one data point, what happens? Over here, where I haven't really seen data, I still am back at my prior. I don't know anything. As I get closer, I start to get more confident about what the latent function is. This is my belief about, this is my posterior mean about what that latent function is. This dashed line is the true latent function. So as I collect more data, I get more certain, okay? What am I doing, right? This is the process in a cartoon of scientific inquiry, right? I'm going from an uninformed belief about the state of the world to I'm gathering data and I'm getting closer to the truth. This dark blue line, my posterior belief, is getting closer to this dashed blue line. Right. Questions? Happy so far? Okay. Okay. Let me plant this just for the future. Put it in a different color so you know it's just to hold on to. You can also think about this problem as a linear regression type of problem, right? A linear regression in the basis of this kernel function. By which I mean, if you just call this some weights, beta or v, right? Then essentially what you're doing is you're taking a kernel representation of the data, you're mapping that through some weights and adding a bias. That looks linear regression-y, right? And in fact, if you've done kernel ridge regression and all this stuff, this is like exactly what is happening. The point of a reproducing kernel Hilbert space and Hilbert spaces in general is that they give you linear regression that you can do in a function space. All right, so we call those the representer weights. They turn out to be a thing that we're really going to want to reason about probabilistically. Okay. You might also be wondering, I'm going to talk a lot about inference. You might also be wondering about doing model selection in this, because that's an equally important part. How do I fit my hyperparameters of a model? How do I traverse through the possible model space as I gather more data? Everything I say here today is going to be applicable to that as well. It's just a lot more mechanics. So this paper you can read about this, but otherwise it's Friday. I'm not going to try to do too much math. Okay, so we've got this idea of a Gaussian process, right? We see that it involves a linear solve, right? You remember linear solves once upon a time. They're expensive. The core object, computationally, right, is this kernel matrix, right? This, notice, is a kernel matrix that is number of data points by number of data points, right? So in any modern interesting setting, we've got hundreds of thousands, millions of data points, something like this. Oh, whatever, maybe tens of thousands. It's still computationally prohibitive to work with this matrix. You can form this matrix well enough, take a bit of memory, but it's not too bad. But solving against this, if you remember your linear algebra class, that's a cubic operation. In other words, that is cubic in the size of the matrix n. N cubed is a big number. It grows fast. You can do this. This is what I mean about this object being tractable. It's tractable in the LaTeX notation sense of the word, right? We can write down what we think this is, but it is not tractable in the I want this to finish on a modern GPU in a reasonable amount of time sense. Okay. Notice that the posterior mean, the posterior variance, and this model selection, the likelihood, notice that all of these involve the same object, which is this linear solve. Okay. Now you might say, okay, this log determinant is also cubic. There's a lot of work resolving that to a linear solve as well, right? So just trust me, there's only one problem here, which is solving K inverse times something. Okay. So there is a ton of literature. I mean, it's its own field trying to come up with good approximation methods to do these type of solves. Cubic scaling is just impossible. And so in some special cases, you can reduce this. In most cases, you can't. And so arises some large number of approximation methods. One of the most well used is conjugate gradients. Must we go through conjugate gradients? You can view linear solves as an optimization problem, a convex optimization problem, right? So suppose you have this quadratic function, x transpose k hat x, right? Remember, what we're trying to do is solve k hat inverse y, yeah? This is a quadratic plus this linear term, so this is a good convex optimization problem, right? Now, what is the solution of this, right? Well, the solution of this is k hat inverse y, right? Take the gradient of that, take the gradient of that. Okay, so what have we done? Nothing. Well, the nice thing that we've done here is that you can take gradients of this, right? You can write down a gradient of this. It looks like kx plus y minus mu. That is a gradient in x, right? You can now do gradient descent. Okay, gradient descent, as we know, it works, but it works very slowly, right? So particularly with something as poorly conditioned as a K matrix, right? Because these matrices are quite large and stretchy. They bounce around a lot, right? So this is a very slow operation. The idea of conjugate gradients, which we've all run into at some point, I suspect, is just to take steps in a different norm, right? So instead of taking steps in the Euclidean norm, instead of taking gradient steps in the Euclidean norm, you take steps in the k hat norm. They are k hat conjugate steps. This is essentially a cookbook algorithm that you just write down. As with all fast linear solvers, sort of the whole core point of computational linear algebra is to turn inverse problems, which are expensive, into forward problems of this kind of multiplication, matrix vector multiplication, because that's way cheaper. All right, conjugate gradient comes out looking like this. We don't need to go through the details of this, but the point is this is just absolutely stock and trade, off-the-shelf conjugate gradient. The point I want you to see is one thing, two things, so sorry. One is you take in a k hat and a y minus mu, right? And you do a bunch of forward multiplies, k hat times v, k hat times s, k hat times s, k hat times s, right? So this operation on a forward pass is just a forward multiplication. Also, what I want you to notice is that here, these are all linear operations, right? So it feels like you might be able to propagate a belief through them, right? Rather than doing this pointwise gradient, you might be able to propagate a probability distribution through them. Right? Some people are lost at this point saying, why are we doing this? Because remember, what we talked about was doing approximate inference, approximate computation in a model. Now we're looking at a procedure and recognizing that it looks like something we will be able to push probability beliefs through. Right? This goes back a long way. There's a lot of papers about this. This is how old I am. All right. So back to this. So we said the crystal ball is actually a computing machine, right? This robot is not bad per se, but he's weird, right? By which I mean there are modeling assumptions and choices that the the conjugate gradient method or the whatever, the robot, the computation machine is making along the way. And we have not reasoned about them probabilistically, and we should if we want to stay within this framework. This is not some trivial mischief. What I want to show you, or the point I want to make, is that the statements that we get out become as much about our approximate inference as they become about our model and data. I'll repeat that in a moment because it's crazy. Approximate inference in practice. So here is what I'll call the mathematical posterior. By that I mean if I had infinite compute and I could compute exactly the correct posterior according to the data that I've observed and the model. Now, right, if your model's wrong or your data's wrong or something like this, I'm not talking about that. This is what the right answer should be. That is your true belief state in this kind of crystal ball scientific world. When you use conjugate gradients, which I just showed you, in a standard way, you get something that looks awfully good. You say, okay, great, I can go and operate with that. It's different, but I'm not too bothered by that. Now you use a different method, subset of regressors, a Nystrom method. Don't worry about what any of these things are. These are just very popular methods. Notice that because approximate methods violate the model, they end up making strong statements about inference, right? So here is the truth about this part of the world, right? Here, we have a lot of uncertainty about what the truth is. If you're trying to make a scientific statement based on an X that exists here, you don't know any. You know very little, right? This method, just because of approximate inference, thinks you're very confident about what's going on here, right? So that is a bias and that a poorly calibrated uncertainty that will significantly alter your statement about the world. Variational inference, stochastic variational Gaussian process, if you ever play with that, it has a known issue where what it does to improve computation is it puts inducing points, it scatters them throughout space, and you kind of collapse your inference onto this smaller set of inducing points. You can see that operating here because what happens is you also collapse your confidence, you collapse your uncertainty at those points, right? So you've created these artificial points that are just part of your algorithm where all of a sudden you think you know something about the world you don't. So how do you deal with this? No. Before saying how you deal with it, I hope you just see that this is a problem, right? All of these cases have the exact same model. They have the exact same data. The only thing that has changed is the computation that went into making inference, right? So think about this as the same as you're fitting some diffusion model, like we were just talking about, right? And one of these is guidance, one of these is SMC, one of these is HMC, one of these is some other thing, right? That's a problem, right? The density that you end up with, if you're trying to do something useful with it, really shouldn't change that much. And we treat this as this minor inconvenience, but it's central. This is a toy problem. Okay. Strong statements and different statements about what you know. This is true of this example model, the Gaussian process, but it's true of all probabilistic models. And it's true of lots of models we've talked about this week. I pulled a couple: density estimators, diffusions, max entropy models, BNNs, etc. It's also true, even if you think, well, I'm not doing probabilistic machine learning, so there's probably not that big a deal. It's a little bit of a longer conversation, but the same thing is going through whether you recognize it or not. And we ignore this effect. Okay, let me skip this. This is just in case you thought this was a silly toy problem, which it is a silly toy problem. It's a one-dimensional problem with 10 data points. I did this on a much larger set of data, a much more realistic set, and did this across kind of all of the standard Gaussian process methods, and just shows this just shows that there's a lot of this issue continues in a large way. Okay, editorializing. Why is this AI for science, right? I said this earlier, right? That AI for science, like the ansatz is that data and a model can let us infer something about scientific interest, something of scientific interest, right? We don't normally talk about it so reductively, but that is fundamentally what we're trying to do. And if that's not true, or if there's a hole in that, we should pay attention. The modern AI toolkit brings its own opinions, right? Biases, shortcoming, etc., to the story, right? As this example shows, it's just weak science, right? Where you have something that you're not controlling for. That's just not the way we like to do things. And this is not just about probabilistic machine learning. So let us understand and rationalize the biases of these. Okay. So how to do approximate inference the right way? I was struggling for a long time how to think about this. I thought a lot about an effective likelihood, right? So this computational machine that is going on here, right? Is it changing my likelihood? Is it actually giving me some different observation model for what let's say, how data gives rise to, how a state of the world gives rise to data? Is it changing my prior? So like actually what is happening is my prior belief is different. And what I've and this postdoc convinced me of is that what is actually happening here is, let's think about computation, right? What computation is the calls to your GPU, right? Computation is how data enters your model, right? It is an effective data set induced by computation. What do I mean by that? If you say, look, on disk, like on my SSD, I've got 1 million data points, and then you run an inference method that touches 12 of those data points, right? It is apparent that you do not actually have 1 million data points, right? Like your possession of those data points is cute, but if you've only computed on 12 of them, right, what you're actually representing is a belief state about 12 data points, okay? Computation, just think about it one step further, that's what it's doing. Like computation is the reach out to your disk, it instantiates that compute, it spends some effort on GPU or on CPU, and updates your model accordingly. It is the process by which data gets updated as a belief. So really what we're going to do is we're going to think about this as exact inference, not approximate inference, but exact inference where you get an updated belief given an effective data set. By which I mean, I'm not telling you that I've solved approximate inference and now it's all exact. What I'm telling you is that if you take a set of approximate steps, I will give you an exact statement about what you did, conditioned on a particular data set that is different than the data set that you have on disk. Right? It is the data set induced by the computation.
I'm curious to know how you, like, it seems like an alternative possibility would be like that the form of the likelihood was wrong, and no matter what data set you chose, it wouldn't explain the answer. Does this question make sense?
Sure. Yes. So there is there's a question here about what is the right setting in which to answer a scientific question, right? I'm not addressing that. What I'm saying is, if you have a belief and you have a model for how that belief gives rise to data, then Bayes' rule tells you how to update your belief, right? If your prior belief is wrong, or your data is wrong, you're going to get a bad answer, right? But all of that is an exact bad answer, if you like, right? So model misspecification, that is a hugely important topic, and one that we work on in its own way.
Specifically here, like in the sense that, like, I think what you're saying is that I can account for whatever happened in the robot non-magic ball by saying there at least exists some data set I could have observed, such that if I'd done exact Bayesian inference through the magic ball, I would get the same result I'd seen through my approximate inference.
That's right. That's right.
And so I guess I just don't, is that like provably true? Like because it seems to me an alternative would be that there does not exist such a data set if I don't also change the form of the likelihood, for example.
Those will turn out to be the same, as in I will show you that essentially what you're doing is a transformation of this data set. And so if you want to call it transformation of the data set, a different likelihood? Sure, it is. It's a projected likelihood. If you want to call it the same likelihood on a different data set.
I might talk to you further later. So
Yeah. The thing that I want to emphasize is the thing that I want to tweak about what you said is that you said I could imagine a data set that would have given me this exact answer. That's not, we're doing something a little more precise than that, which is saying, given the steps that you took, this is the exact data set that you actually used.
Oh, like you're going to give us a constructive algorithm?
Yeah. Oh, wow. A constructive algorithm that results in, essentially, you thought you had 1 million data points, right? We went through this kind of toy example where you got 1 million data points and you just took 12 of them, right? But if you do, let's say, 12 conjugate gradient steps, we can show you that what you end up doing is taking a particular set of linear projections of your data set. So it's like the 12-dimensional projection of this 1 million data points, if you like.
This will be specific to conjugate gradient in this case.
Not conjugate gradient. This will be specific to this example model, the Gaussian process. There are extensions of that, but some of the tools we will use here are very, and this is kind of the comment I made about linear algebra before. Some of the tools that we will use here are absolutely based on our ability to propagate uncertainty through linear algebraic operations. And that gets trickier when you want to do some like latent Dirichlet allocation model or something like that, right? Not impossible, but just, yeah, I'm happy for that to be a shortcoming of this, right? This is not like once you do it here, you can just do it anywhere kind of thing. All right, so effective data set, right? Iterative numerical methods take linear combinations of data. This is true in Gaussian processes. This is true in lots of methods, modulo what I just said to Jen. We're going to define the set of actions taken by an approximate solver as this matrix, right? So you take I actions. Each of those is some projection of your n data points. I showed you in S very briefly in the conjugate gradient method before, but let me give you kind of other examples of that, right? So in conjugate gradients, I showed you this S matrix, which is essentially the residual as you go through and take these conjugate steps. If you do a Cholesky factorization, essentially you're doing this in canonical order through the data set. If you do an eigenvalue decomposition, right, or a partial eigenvalue decomposition, essentially you're traversing the eigenspace of the kernel matrix and using projections that way. Inducing point methods, Nystrom methods, subset or regressor methods, all of these end up taking some basis according to an inducing point. That's quite a bit harder to see, but just allow it. Okay. I'm gonna establish that connection further later. It's just it's pretty detailed, so I wanted to give the punchline of it first. So we talked about this Gaussian process posterior before, right? And then I said, look, instead of having a data set Y, you're gonna have a projected data set, an effective data set, SI transpose Y. Okay, so that, because this is a linear operation, you can push this through Gaussian inference. In other words, now instead of Y given F is normal under F and sigma, you have S transpose Y. These are just Gaussian identities, right? S transpose F, you project your function, your mean function down, and you project your variance. The posterior that gets induced is also projected. It maintains the same form, now with just a different covariance matrix. Okay, this is an inverse covariance matrix. Call it a precision. It essentially looks like this. So notice that this is a S projection of your kernel matrix. If this thing were the identity matrix, you would recover the original stuff. So what you end up getting is combined uncertainty. Okay, this is in many ways the punchline of how you reason about approximate computation. Before, we had always talked about mathematical uncertainty, right? This is the true object that in the limit of infinite computation, I can say I have some a priori uncertainty. And what happens is, based on my observations that happen at these points x, right? I invert this matrix, multiply that through, and that reduces, in this kind of Schur complement way, that reduces the amount of uncertainty that I have. This is my posterior uncertainty, my mathematical posterior. But I recognize that because of taking approximate computational steps, I have to add something back, right? Which is the computation that I haven't done. This is what I mean by this being constructive, is that you end up with the following representation. I mentioned these representer weights before. This turns out to be exactly the uncertainty on the representer weights, which it says in this linear regression analog, it says, look, if you have Bayesian linear regression, probabilistic linear regression, right? You have some prior belief on your betas, on like those linear regression coefficients. What you're going to do is you're going to go ahead and update that through. And over time, as you collect more and more data, you will increase your confidence. So this is a nice outcome, right? What you get out is combined effective uncertainty that is a result that is a result of both having finite data, mathematical computation, and finite data, right? So mathematical uncertainty plus finite computation, computational uncertainty. That is appealing in the sense of that's the way the world should work, right? You have some limited amount of data. You have some limited amount of computation. Both of those have the effect of reducing uncertainty. And the way you combine those two, or the way you invest in those two, will reduce your uncertainty differently and in different places. I mentioned this expression, data is as data does. In so much as this is a workshop and it's Friday, I think it's okay to kind of wander for a moment. We think about data as this existing object, right? But what I've been trying to convince you with this whole discussion of your SSD versus your GPU, right, is that data only influences your model to the extent that you use it, to the extent that you consume it, right? And it's computation that consumes your data, right? And so if you don't consume a data point, or if you only consume part of a data point, part of the information that it has to tell you, you only got part of that data point. So data is as data does. Okay. Computation and data are a little bit more fungible concept than we might have thought them to be.
So you can compute C?
You can compute C. You can't compute either of these, right? Or rather, this object takes all the computation to compute. So I will show you how to compute this. These, you know they exist, and I will go to the trouble of computing them so you can see them. But in effect, the algorithm that I will present will only compute this. Yeah, but you're spot on, right? Like it is impossible to imagine that you could compute this and this, because that would be the same as computing this, right?
Sorry if I just missed this earlier, but this is about the uncertainty that comes out of the Gaussian process model.
Yes.
Associated with the x's that you put in.
Yep.
What about just the point prediction value, the mean value?
Yes. Those are linked. This is a great question. Thank you for raising it. Those are absolutely linked through this, right? Which is, it's the uncertainty that tells us how much we should trust an observation, and thus the mean depends on it. Okay. So that you're absolutely right to point this out. This is not just a statement about calibrated uncertainty. Sure, we all love calibrated uncertainty, but mostly we care about mean estimation, right? Like we are point estimate people at heart. So no, this absolutely has an influence on that, and we'll see that kind of in results. Okay. So we looked at this before, right? This was approximate inference in practice. Here's a new way. We're going to sequentially update data points. So in this example, this is just the original toy example I showed with 10 data points, right? So here's a an odd way we could look at this. We could look at this as saying, this is the example where I say you have 1 million data points, you only look at 12 of them. What I'm going to do is I'm going to look at that and saying, look, I have these 10 data points, but I'm going to look at them one by one, and I'm going to track the computational uncertainty. So when I have that first data point, remember this was the variance that I had, right? That variance is made up of this amount of mathematical uncertainty in blue, right? This is just the marginal variance, a little easier to look at, plus all the computation that I haven't done, right? So Jen, this is your green plus blue, right? Because I can calculate in this toy example, I can get you the blue, I can get you the green. As we add more data, of course, the mathematical uncertainty, which is conditioning on all 10 of these data points, does not change. But what you can see is that as you add data, you are spending computation to reduce your computational uncertainty in various places. Your effective data set is growing. You continue to do that until you have effectively conditioned all your data, and you are left with exactly what we started in the first place, which is the true mathematical uncertainty. There's no computational uncertainty left because you've spent all the computation you needed to. You can see this in other methods. That was just exact inference, but I can show you this now on these same 10 data points with just the number of iterations that you take through a particular method. So this is a Cholesky factorization, and you can see that as you evolve, you are reducing computational uncertainty. You are reducing it at a different rate in different places per different approximation algorithm, to the point of we're not solving how to do approximate inference here. We're telling you if you're doing approximate inference, this is the actual uncertainty that you should represent, right? I hope that's not unsatisfying. Same thing with conjugate gradients. So this is what I was saying about I hope this is not unsatisfying, is that remember before how we said that conjugate gradients and Cholesky and all these were making different assumptions about the world? All we are doing now is making clear what those assumptions are, right? You can see that these have different posteriors now in different computation. I mentioned that I'll skip this. I finished at 11:30, right? I'll skip this. Okay. Yep. Here's the answer to your question, right? Or I gave you the answer to your question. Here's a picture. So you might be concerned that this is just a story of uncertainty. This is negative log likelihood, right? Which is some combination of mean squared error and also uncertainty, right? Like your log determinant envelope. So it does a much better job in uncertainty estimation, right? This is ITER-GP, what I just showed you, versus kind of the baseline standard or the gold standard of approximate inference. So by having, in this case, less overconfidence, which is a weird thing to say, but let me be clear about what that means. What we showed is that approximate inference methods, because they are bringing extra biases, they can only reduce your posterior more than it should be. They reduce your uncertainty more than it should be, right? Because they are overconfident. So what tracking computation does is it gets you back to a properly calibrated and sort of theoretically provable, more accurate uncertainty. That uncertainty will then benefit you in generalization. You can see it here in variance, but it's also a mean phenomenon. So this is just looking at the mean squared error. Because of exactly the equation I showed you, it works better as well. Yep. What's that? Yeah, this is like the weakest protein, right? This is the UCI dataset protein, right? Which, like, I don't know what that actually involves, but it's just called protein. Yeah. I mean, if it makes you feel any better, one of them is called KEGG, so it's like we're like at that level, right? Yeah. Okay. So I think I've made these points already. The result of this is if you update your Gaussian process or your model via matrix vector multiplication, then the combined uncertainty of this algorithm is precisely the correct object to capture your belief. I didn't show the theory behind this, but I do mean precisely the correct object. It is it is provably correct. Little bit of technical details. I mentioned this weight space view, right? Where essentially these are the representative weights. These are the betas in that linear regression. If we represent uncertainty on that, that is, it turns out exactly what we're doing, right? If you know the representer weights, right? So suppose you knew these exactly. Well, then you're finished, right? Because you have completed the linear solve, right? So the problem of doing true uncertainty, true posterior inference, exact posterior inference is completed. But you don't. Now suppose you're on the other end of the spectrum, which is you have no knowledge whatsoever of these representer weights. Then it turns out the right prior to endow these representer weights is this, and you recover the prior from that. In other words, it is how much you know about these coefficients that exactly is monitoring how far you've moved from the prior to the posterior. So as you do computation, if you can update your belief state about these using the computation that you've done, that is exactly tracking you from prior to posterior. That's a weird way to think about Gaussian conditioning, but it turns out to be the right thing. Okay. There's a lot to get through. Hold on. No, this is way easier. What all of this math comes out to is an algorithm that iteratively walks through constructively updating and creating this C matrix that we mentioned before, which is the combined uncertainty. Right? So how it does that is by creating a belief state on these representer weights, right? These VIs. It walks through as you take your linear updates, as you take your actions at SI, which I gave you a table for different iterative solvers, Cholesky, conjugate gradients, et cetera. None of this, in other words, depends on conjugate gradients. This is a call to a conjugate gradient method, right? Or a call to a different, like pick your iterative solver of choice. As long as it spits out actions, you might call it a policy. Connections there for another talk, right? As long as it spits out these actions, you will walk through this and update both your computational uncertainty, excuse me, not your computation, you update your combined uncertainty, which is in effect updating both your posterior and your computational uncertainty. I apologize for jumping through that, but that.
Are you able to give a bit of intuition about how this is, how it's getting that?
Yeah.
Beyond the intuition you gave.
Yeah. So I told you how when you have no belief, when you have no updates to your representer weights, you essentially have an uninformed prior, and that returns the prior of the Gaussian, right? You haven't seen enough data yet. When this is reduced to zero, you have solved the problem exactly, so you're finished. So all of these methods depend on a residual, right? Like they depend on some error term to do their to query their policy. So what you have is this residual, which is your data minus your representer weights, which is your belief about how much you've solved this problem already, propagated forward, right? This is beta times k, right? That error, that error is a linear term. You are then going to take a linear inner product with the action that your policy gives you. So that's all linear, and you can just push your variance right through that, right? That gives you an update, right? And you just walk through updating. That's what I mean when I said it's all linear algebra, right?
Just ask a clarification question. So we're talking about the representer weight uncertainty.
Yes.
It's kind of in the spirit of like probabilistic numerics, like exact inference would kind of go to zero with perfect computation.
Yes. So this is yes, this is absolutely an example of probabilistic numerics. That example is made plain in that. The reason I go at it from the other direction here is because this, I think, with all love to the probabilistic numerics community in which I'm a part, this is a place where solving this problem requires you to use probabilistic numerics, whereas often probabilistic numerics people think, because I want to do this, right? And this is like, you are required to do this, yeah. But no, those connections are, there are commented out slides in here that draw that out entirely. All right, we went. Okay. Okay, so here's this in one final picture. The mathematical uncertainty of this method, of this model and this data looks like this, right? The computational uncertainty depends on where we have spent compute. So I've colored these data points red for whether they've been touched more by the method, touched more in the SI transpose Y sense, right? So what you can see from that, and this is just for conjugate gradients in the big box, and then here's some others you can look at. It's the same story over and over again. But what you can see is that in places where you've hit this a lot, there is lower computational uncertainty, which confers lower uncertainty out here. Whereas here, these data points, which you haven't actually looked at, even though you think you have, right? These still have these have close to prior uncertainty around them because they haven't been hit by the computational method, right? Some other time they might have been, some other random method they might have been, but that's the coherent statement we were trying to get to. Oh yeah, here you go. Here then, approximate inference the right way and probabilistic numerical treatment of representative weights are shown to be identical. Yeah. Okay. Final bit. Approximate inference should be taken into account in probabilistic machine learning. Today we've done that for Gaussian processes. Absent doing that, computational uncertainty is ignored, and I hope I've convinced you that it is surprisingly significant. Yeah. It is changing your belief about the world in ways that you're not paying attention to. Data is as data does. In a very concrete sense, so data is as data does, like smart is as smart does, stupid is as stupid does. Depending where you come from, you might have heard this statement before. The idea is that like these are not immutable properties. Like data is not an immutable property of the world. It is what you do with it that counts. In a very concrete sense, this shows mathematically that data only exists to the extent that you use it, which is fun to think about. Some other questions you might have. What other inference settings admit this? This is kind of Jen's concern. This is all of our concern about how specific what I've showed you is to Gaussian processes. The problem is absolutely everywhere. The solution that happens to be based on a lot of linear algebra is very specific to Gaussian processes, right? How do you push this through to decision theory, right? If you want to pay attention to this, we've written about a paper about this, using this for Bayesian optimization. How to use this for computational neuroscience, I could have talked about that, but already. Active learning, I think this is really cool because I've shown now that data and computation are actually fungible, right? And this is something that scientists actually care about, right? Because we don't just work with ImageNet. Like there's actually a cost to collecting new data. And you have an active exchange space. There's an exchange rate between collecting data and spending more computation. Like you can precisely answer the question, should I buy a new GPU or should I get more experimental time, right? Which is a fun thing to think about. Great. Thank you very much. Sorry for taking a little too long.
I have questions too, but I've been asking them all the time.
Thank you. So in the weight update view of this,
Yep.
where you're allocating resources to some data points, is that giving us a useful way of prioritizing among data? So I might say, if I have some measurements that are very close to each other, I should spend as much time on that set and I should allocate my resources to ones that are further away. Or if I have experimental errors and some of those error bars are larger, I should deprioritize spending resources on those points. Is that sort of what IterGP is able to do for us?
Yes. So in some sense, already the approximate inference methods are trying to do that, right? Because they are not just like, for example, that is the difference between doing gradient descent and doing conjugate gradients, right? Is you're taking a step in a conjugate norm, which is hopefully saying, look, if I just looked at this data point, which is one direction in Euclidean space, I don't need to look at this other data point, which is another direction in Euclidean space, but it's actually almost the same direction in k-hat conjugate space. Yeah. So the reason I do that preamble is to say, like, this is not exclusive to the ITER-GP. Like, this is everywhere. But yes, you are absolutely right from the extent of you are seeing as you progress through where you are getting where your combined uncertainty is largest, and then you can. This is part of the kind of active online programming. You can query data in places of large uncertainty, or you can spend more compute in places of large uncertainty. That is a tool you now have. We have used that for, I mentioned this Bayesian optimization problem. You could imagine doing exactly that in Bayesian optimization, where you say, look, what I'm interested in is finding regions of high utility. And so I'm going to spend my updates there, like I'm going to allocate compute according to that. But it's absolutely the right way to be thinking about that.
Thanks. I was curious if this gives you tools to say, given a fixed compute budget, which of these different approximate inference algorithms are going to like minimize my combined uncertainty the most, and if that gives you insights into, like, for your particular data set, which approximate inference methods to use.
That's a cool idea. It's certainly, okay, trivially speaking, yes, it would do that, because if you could evaluate combined certainty, but the question is actually, well, wait a second, you just spent number of methods times that computation, so how could you actually do that in an online way, like choosing between them?
Or maybe for particular problem domains that you're interested in, where you collect data sets in certain ways and, you know, have certain types of things you could ask. Are certain variational inference methods better suited for these types of problems based on this analysis?
So I mentioned here, that we query a policy, right, where we select the action. So one thing that you could imagine doing, one thing that we have done is to say, well, wait a second, can I differentiate through this based on where I'm collecting my data, such that instead of doing this kind of mixed integer programming question of like, which of these methods should I pick at different times, I'm actually just letting the data tell me what my policy should be. That is definitely a thing we can do. That's the way we've approached that question so far. So that's the only thing I have a coherent answer for. But it is definitely something we've been thinking about in that regard.
Just to clarify, what you mean is the policy encompasses like all the approximation methods and it can switch between them?
Apparently, what the policy's job to do is to say, I want to look at the state of the world, which is typically for a policy like this, it's looking at residuals, right? It's saying, like, which directions have I searched and how small is the error in that direction? And it is making an update based on that. Like, that is like, we don't normally think about an eigenvalue decomposition as doing that, but like if you do Gauss-Seidel elimination, like that's just like precisely what it's doing. Like you're walking through that, coming up with new eigendirections to operate on, right? Conjugate gradients does that same thing with residuals in the conjugate direction. There's no reason why you can't differentiate through that as you are differentiating through this whole procedure to different hyperparameters that exist in here to do exactly what he's asking for.
This is really cool. You mentioned earlier about like model selection, how this can also be used for that.
Yep.
Just want to know if you could elaborate a bit more and possibly also just like extending that model selection space to not just GPs, but other models. But like,
yeah, I can elaborate on the first part of that question, not the second part of that question. Or, you know, over coffee, I can elaborate on the second part of that question, but it is like, is way past a grain of salt. It's like a whole salt mine worth of that. So where are? Sorry, I'm looking for the model selection piece. So essentially what we're trying to do here is maximize this likelihood objective. So now, first of all, if you believe that we can propagate uncertainty through this, there should be no trouble in propagating uncertainty through this, right? So just doing that is okay. The problem that comes up, and the real issue with doing model selection, is that, remember I was talking about the effective data set, is what you end up doing is, naively, if you just try to push IteraGP through this, you end up doing approximate inference, you do model selection on the effective data set, which turns out to be a really bad idea, because then all of a sudden you're almost ending up in a pathological case of what you were asking for, which is you're saying, find me the model that agrees most, or I'm going to look for data that agrees, that gives me like the most certainty about that. So you do a terrible job on all your other data. So what you end up having to do is coming up with a new objective function that basically maintains fidelity over the whole data set rather than just on the effective data set. That is the means by which we extend this to model selection. But then the actual operations of propagating uncertainty through this type of object is exactly the same thing. And you can do that the same way with stochastic trace estimators, which end up looking exactly like that, just with different basis vectors. That's a 2-minute explanation of how you push that through. That brings up some computational issues of its own, which we have ways to deal with. And there's a paper not referenced here that I can send you to give you all the specifics on that.
I think in the interest of time, we got to wrap up here, so we have time for lunch, and then we'll reconvene at 1:30 to hear the critique of this.
Thanks, everybody.